minus 160 degrees Celsius, barely 30 craters. When NASA first photographed Europa, they saw a frozen, dead world. Scientists moved on. Then the Galileo spacecraft picked up a magnetic signal that should not have been there, the unmistakable signature of a global saltwater ocean hidden beneath kilometers of ice. What NASA has actually found on Europa rewrites what we thought we knew, and the full picture is still emerging. Voyager 2's cameras captured Europa in July 1979, sending back images that seemed to confirm the moon's reputation as a frozen outpost. The surface, dazzlingly bright, reflected nearly two-thirds of the sunlight that reached it, more than any other of Jupiter's major moons. The photos revealed an icy crust with almost no relief, a world painted in whites and pale blues, interrupted only by faint brownish lines. Unlike the battered faces of Ganymede or Callisto, Europa's shell was nearly spotless. Only about 30 craters larger than 4 kilometers could be counted across the entire globe. For planetary scientists used to reading the scars of ancient impacts, this scarcity was startling. On Earth's moon or Mercury, a dense field of craters signals a surface unchanged for billions of years. Europa's smoothness hinted at something different, a surface that had been wiped clean in geologic terms, perhaps only 40 to 90 million years ago. Temperature readings deepened the mystery. Instruments measured a global ceiling of minus 160 degrees Celsius, colder than the coldest places in Antarctica. Even at midday near the equator, the ice never warmed above minus 130 degrees Celsius. With so little warmth and no sign of volcanic activity, early mission reports described Europa as a static ice ball, its crust perhaps 100 kilometers thick and frozen solid from pole to pole. The lack of mountains, valleys, or obvious surface activity seemed to confirm the verdict. Europa was a relic, a world where nothing had stirred for eons. Yet the very features that suggested lifelessness, a spotless surface, extreme cold, and a youthful crust, quietly posed questions that Voyager's cameras alone could not answer. Magnetic data from the Galileo spacecraft changed everything. As Galileo made its close passes over Europa between 1996 and 2000, a team led by Dr. Margaret Keivelson at UCLA watched the magnetometer's readings with growing surprise. Instead of a steady background, the instrument detected a magnetic field that shifted in both strength and direction, closely tracking Jupiter's own powerful field, but with a measurable lag. This was not the signature of a solid, inert body. The pattern matched what would be expected if a vast, electrically conductive layer lay beneath Europa's icy shell, something like a global ocean of salty water. The team began to model the data. They compared the amplitude of the magnetic perturbations and the phase lag, how much the induced field trailed behind Jupiter's rotation. The numbers fit best if Europa contained a shell of water about 100 kilometers thick, with a conductivity near 0.1 Siemens per meter. That level of conductivity is not possible for pure ice or rock. It requires a briny liquid, similar in composition to Earth's seawater. The fit was so precise that other explanations, such as a thick ionosphere, localized brine pockets, or unusual rocks, quickly fell away. Only a global ocean could account for the magnitude and timing of the signal across multiple flybys. In late 1997, the Galileo MAG team's lab notebooks recorded a moment of realization. The induced field's amplitude and lag matched what would be expected from a conductive ocean. Peer-reviewed papers soon followed, and the planetary science community began to accept that Europa was not a frozen relic, but a world with a hidden, global sea. The evidence was invisible to the eye, but unmistakable in the data. A magnetic handshake between Jupiter and a buried ocean, sensed from millions of kilometers away. Hints of water vapor venting from Europa's surface have sparked one of the most contentious debates in planetary science. In December 2012, the Hubble Space Telescope (STIS) instrument recorded a faint ultraviolet brightening above Europa's southern limb. The data suggested a plume with water vapor column densities between 10 to the power of 14 and 10 to the power of 15 molecules per square centimeter, rising nearly 100 kilometers above the ice. A second set of Hubble observations in 2016 found 3 more such events, but each was brief and barely above the threshold for statistical significance. Over the next several years, teams scrutinized the raw images and calibration pipelines, searching for artifacts or background sources that might explain the signals. Critics pointed to the geometry of the observations, Europa passing in front of Jupiter's bright limb, and to the risk of sub-pixel misalignments mimicking a true plume signature. The controversy deepened in 2018 when a reanalysis of Galileo's 1997 flyby data identified a 2-minute thermal spike, consistent with a spacecraft fly-through of a concentrated vapor column. Yet the duration and intensity fell short of the sustained, high-density plumes seen at Saturn's moon Enceladus. Ground-based telescopes, including Keck and VLT, failed to confirm any repeatable plume activity, setting upper limits well below the original Hubble claims. Today, the evidence for intermittent venting on Europa remains unresolved, tantalizing but not conclusive, and a driving reason why direct sampling remains a top priority for future missions. Galileo's solid-state imaging system delivered the first detailed look at Europa's fractured landscapes. In places like Connemara Chaos, the surface breaks into jumbled blocks, some as large as 20 kilometers across, tilted, rotated, and scattered like ice flows in a frozen sea. These blocks rest amid darker, finer-grained material, filling the gaps where the original surface shattered and moved. Planetary geologists studying these mosaics notice patterns that couldn't be explained by surface impact or slow erosion alone. Instead, the evidence points to active reshaping from below, warm ice or briny slush welling up, weakening the shell and causing the crust to collapse or rise in great swells. 2 main models compete to explain how chaos terrain forms. One suggests diapiric upwelling, where buoyant, partially melted ice pushes upward, distorting and cracking the overlying shell. The other favors collapse, where pockets of liquid water or brine drain away, leaving the surface unsupported so it breaks and sags. Both mechanisms require the ice shell to be relatively thin and dynamic, not a rigid, ancient crust. Multiple lines of evidence, from tidal flexure calculations, magnetic induction, and impact crater modeling, converge on a shell thickness between 10 and 30 kilometers. That's thin enough for material and even surface chemistry to potentially move between the ocean and the surface, setting the stage for further exchange driven by Jupiter's relentless radiation. Jupiter's magnetic field sweeps past Europa with relentless force, bombarding the moon's surface with high-energy electrons and ions. Instruments on Galileo and Juno have measured an annual radiation dose near 5 times 10 to the 8 raids on Europa's leading hemisphere, a level that would destroy unprotected organic molecules in hours. To astrobiologists, this radiation is both a curse and a potential gift. The surface ice, exposed to such extreme flux, undergoes constant radiolysis, and water molecules are split apart, forming molecular oxygen, hydrogen peroxide, and a suite of reactive radicals. Laboratory experiments simulating Europa-like conditions show that oxygen can reach concentrations of about 0.1% in the upper ice, while hydrogen peroxide builds up to nearly 0.5%. These oxidants are hostile to life at the surface, but if they can be transported downward by slow-moving ice convection or melt-through events, they could reach the subsurface ocean. Theoretical models suggest that this delivery might provide a steady chemical energy source, fueling redox reactions far below the irradiated crust. Yet the true rate and efficiency of this oxidant transfer remain unmeasured. Without direct sampling, the possibility that Europa's ocean is chemically energized by surface radiation stands as a hypothesis, one that shapes the search for habitability, but still awaits confirmation. In 2023, the James Webb Space Telescope delivered a new layer of evidence by mapping carbon dioxide across Europa's surface. Using the NIR-SPEC instrument, the Webb team measured a band depth for carbon dioxide near 5%, an unexpectedly strong signature. What stood out was the clustering of this carbon dioxide in specific regions, concentrated along the chaotic terrains and trailing hemisphere lineae, areas already suspected of active exchange between the surface and the ocean below. The spatial correlation raised the possibility that some of this carbon dioxide may be sourced from the interior, rather than simply deposited by radiation or micrometeorite impacts. While the debate continues over whether these patches reflect internal outgassing or surface processing, the Webb dataset has sharpened the case for ongoing chemical cycling between Europa's ocean and its frozen shell. Despite decades of investigation, many of Europa's secrets remain out of reach. No spacecraft has directly sampled its subsurface ocean, and every conclusion about its depth, salinity, and chemistry comes from remote sensing and indirect measurements. There has been no confirmed detection of life, nor any biosignatures that would indicate biology at work beneath the ice. The hints of water vapor plumes, suggested by Hubble and debated in Galileo's data, remain unresolved, with no repeatable or unambiguous plume event confirmed. The true abundance of ammonia, a key chemical that could alter the ocean's properties, is still unknown. Even the possibility of active surface-ocean exchange rests on circumstantial evidence. Each of these gaps defines the limits of current knowledge and sets the agenda for future exploration. Europa Clipper, set to launch in 2024, is designed to answer the questions that have lingered for decades. The spacecraft will perform more than 40 close flybys, some passing just 100 kilometers above Europa's surface. Its instrument suite includes Reason radar to probe the ice shell, MASPEX and SUDA to analyze particles and vapor, UVS to search for plumes, MAG to refine ocean conductivity, and eThemis to map thermal anomalies. These instruments will target the mysteries left unresolved by earlier missions. While Clipper cannot drill through the ice or directly sample the ocean, its coordinated measurements will bring the search for habitability into sharper focus when it arrives in the early 2030s. Europa remains an enigma, a world with hard evidence of a hidden ocean, but no confirmed sign of life or direct ocean sampling. As Europa Clipper prepares to launch, the next decade may finally turn speculation into answers. Sometimes, science advances not by certainty, but by persistent, disciplined doubt.